Students, this is a video on finding real roots of polynomial equations. It's a little bit of a tricky lesson, so we'll see how it goes with the video. All right, so the first thing I did was take something out of your textbook because I wanted to talk through it. Sometimes a polynomial equation has a factor that appears more than once, and this causes a multiple root. For example, in the graph on your left, 3x to the fifth plus 18x to the fourth plus 27x to the third has two multiple roots, 0 and 3. And for the root 0, the 0 is a factor 3 times because it has a factor of 3x to the third. We can factor 3x to the third out of all three terms. Let's just kind of look at factoring it for a second. So if we factor it, I factored it here below. I pulled out a 3x to the third, and I'm left with x squared plus 6x plus 9. So I get factors of 3x to the third times x plus 3 squared. And now you can see really clearly that 3x to the third we get a factor of 0 3 times, and from x plus 3 we get a factor of -3 twice. What happens when we have multiplicity of a root? When we get a root multiple times? What it does is that means our graph will touch the x-axis but not cross it. And when we have a multiplicity of 2, that means our graph will basically sort of bounce off the x-axis. It will touch it, it will reflect off the x-axis, I guess is a better word. It will reflect off the x-axis. When there's a multiplicity of 3, the graph bends near 0, 0. Okay, so you can see that here. Another really simple example would be f of x equals x plus 2 squared. If I were going to graph this, I know that the vertex is at -2, 0, and there's no dilation, so it goes to the right 1, up 1, to the right, to the left 1, up 1 from -2, 0, and then it has a point at 4 on the y-axis. At any rate, it looks like this. So you can see that it has a multiple root at x equals -2 and reflects off the x-axis. So there's a couple of different examples. Hopefully this idea is clear. So we're going to take this, I chose kind of a challenging one. Some of the other ones in your homework you're going to be able to either use difference of cubes or sum of cubes, or factoring by grouping to factor. This one's a little trickier, so took me a little while looking at it, but I noticed that there is an x to the fourth and there's a 16, and that I noticed that 8, 24, and 32 are all factors of 8. So I'm going to guess that x minus 2 is a factor. And I'm going to check this out by, I think it's a possibility that since that x minus 2, it might be x minus 2 to the fourth, because -2 to the fourth is 16, and x to the fourth is x to the fourth. So I'm going to try this out and see if, using my synthetic division, to see if 2 is a factor. So here we go. I've got 2 times 1 is 2, -8 and 2 is -6, 2 times -6 is -12, 24 minus 12 is 12, 2 times 12 is 24, -32 and 24 is -8. 2 times -8 is -16, 0. When I get 0, I know that there's no remainder. I know that x minus 2 is a factor, and I'm left with x to the third, 1x to the third, right, minus 6x squared plus 12x minus 8. And looking at this is going to be a difference of cubes. So our difference of cubes here is x minus 2 cubed, and then we also have our 2 here, so that's times x minus 2, and that factors into x minus 2 to the fourth, which means we have a real root of 2. We'll write root equals 2 with a multiplicity of 4. Okay, so that brings us to our rational root theorem. We can't always factor polynomials easily, and so there is a way that we can take an educated guess at what might be some of the roots, and we can try them out with synthetic division to see if they work, kind of like we did on the last problem. So the rational root theorem, but a little more organized. The rational root theorem says if the polynomial has integer coefficients, then every rational root of the polynomial equation p of x equals 0 can be written in the form p over q, where p is a factor of the constant term of p of x, and q is a factor of the leading coefficient of p of x. So let's give this a try. Let's look at this problem. A shipping crate must hold 12 cubic feet. The width should be 1 foot less than the length, and the height should be 4 greater than the length. What should the length of the crate be? Okay, so let's give it a length there. The width should be 1 foot less than the length. We'll call this the width, so L minus 1. And the height should be 4 greater than the length, L plus 4. What should the length of the crate be? And it must hold 12 cubic feet. Okay, so we have, let's change L to x. Let's have x equal the length. And just easier to read here. So we have x times x minus 1 times x plus 4 equals 12. And multiplying together, we get x squared minus x times x plus 4 equals 12, and x to cubed plus 4x squared minus x squared, that's a minus x squared minus 4x equals 12, or x cubed plus 3x squared minus 4x minus 12 equals 0. And let's just bring that, well, we can bring this down. Okay, and we want to factor this. And we can't, certainly not a sum or difference of cubes. And we want to figure out what are some possible so we know that all the possible factors are p over q, where p is the constant and q is the leading coefficient. Constant is negative 12, right? All the factors of negative 12 over all the factors of 1. Well, that makes it easy that the leading coefficient is 1. Okay, so we're looking for, since it's over 1, we're really looking for what are all the possible factors of negative 12, and we have, factors of 12 are 1 and negative 1, so we'll write that as plus or minus 1. 2 is a factor of 12, so we have plus or minus 2. 3, plus or minus 3. We have plus or minus 4. And we have plus or minus 6 and plus or minus 12. Since 1 is the denominator, we don't really need to include it. But if it was something different, obviously we'd have more possible solutions. So we have to decide to try something out here. And I always think 2 is a good place to start, so let's try that out. We have our, let's go ahead and set up our synthetic division. So we have, let's set up a 1, and we have 1, 3, negative 4, and negative 12. We bring 1 down. 1 times 1 is 1. 3 minus 1 is 2. 1 times 2 is 2. Negative 4 and 2 is negative 2. 1 times negative 2 is negative 2. We don't get a 0. So let's just erase that. We tried 1. Let's try 3. See what happens there when we try 3. So 3, and we have 1, 3, negative 4, and negative 12. We bring our 1 down, and we have 1 times 3 is 3, 0. 3 times 0 is 0. Negative 4 times 3 is negative 12. Seems like maybe negative 3. Oops, I did something wrong. Let me go back here. Oops, I went back a little bit too far. Negative 4 and negative 12. I think I added something wrong. All right, 1 times 3 is 3. 3 and 3 is 6. 3 times 6 is 18. Negative 4 and 18 is 14, and that's, we're not going to get a 0 there. So let's try again. Let's try with a 2. See where we get with that. 2 and 1, 3, negative 4, negative 12, and we get 1 times 2 is 2. 3 plus 2 is 5. 2 times 5 is 10. 6, 2 times 6 is 12, and we get a 0. So if 2 is a solution, a factor then is x minus 2, and we are left with x squared plus 5x plus 6 equals 0, and we can factor x minus 2 into x minus 2 times x minus 3 equals 0. Negative 2 times negative 3 is 6. Okay, so that works. So we do have a factor of, we do have 2 as a solution and 3 as a solution. So our solutions are 2 with a multiplicity of 2 and 3 with a multiplicity of 1. Okay, last theorem here, the irrational root theorem. If the polynomial p of x has rational coefficients and a plus b root c is a root of the polynomial equation p of x equals 0, where a and b are rational and root c is irrational, then a minus b root c is also the root of p of x equals 0. What that's really saying is what we said earlier in chapter 2, is that roots come in conjugate pairs. So if a plus b root c is a root, then a minus b root c is also a root. And you'll see this when we go through the quadratic equation here. So let's look at this. Quadratic or this polynomial equation. We're trying to find roots. Doesn't look easily factorable. So what I'm going to do is look at again p over q, and that means negative 4. All the factors of negative 4, so plus or minus 1, plus or minus 2, and plus or minus 4, all over plus or minus 1 plus or minus 2. So actually, let me think, 2 Yeah. Okay. So I'm going to, instead of taking up lots of video time, we're going to try -1/2. I tried a few others before I got to that, but we're going to use our synthetic division. 2, -3, -10, -4. And we bring down our 2, and -1/2 times 2 is -1, -3 and -1 is -4, times -1/2 is a +2, -10 and 2 is a -8, times -1/2 is a +4, 0. So we know that x plus 1/2 is a factor. Remember, if a solution is -1/2, then our factor is x plus 1/2. And we're left with 2x squared minus 4x minus 8 equals 0. We can factor a 2 out of that, and we get x plus 1/2 times 2 times x squared minus 2x minus 4. And we'll never get anything that multiplies to -4, two factors that multiply to -4 that add to -2. Positive and -2 would be 0. Positive 4 and -1 would be 3. -3 and +1 would be -3. So we're going to use the quadratic equation on this simpler quadratic here. And we get x equals -b, which is, in this case, 2. -b would be -2, plus or minus square root of b squared, that's 4, minus 4 times a times c, all over 2a, that's 2. And we get 2 plus or minus square root of 4 plus 4 times 16 is 64. 4 plus 64 is 68, all over 2, which is 2 plus or minus, actually let's back up here a second, root 68. 4 goes into root 4 goes into root 68, root 17 times, so we get 2 plus or minus root 4, root 17, all over 2, or 2 plus or minus 2 root 17, all over 2. I can cancel out my 2's. I get 1 plus or minus root 17. Okay, I still need the 1 because when I cancel out the 2's, I've got 1, 1, and 1. 1 plus or minus root 17. So, okay, so my factors all together are, we don't have to worry about the 2 because 2 is never going to equal 0. So -1/2 with a multiplicity of 1. We have, and then we have 1 plus root 17 and 1 minus root 17. And the point of the irrational root theorem is that the irrational roots are always going to be a conjugate pair. And hopefully you guys are familiar enough with that word now. So that is it on this concept. I'm hoping this gets you in good enough shape to come in and do some problems with this when we meet next. Thanks so much.